Cool. I believe we are live. So let's get started. Welcome, everybody, to this month's Rocky Worlds discussions. It's great to see you all here and very excited to hear Diogo Lourenco, who joins us today to continue our series. So, as a reminder of netiquette, please use your full name and keep muted throughout the talk. And when asking questions at the end, please do turn on your video so we can see you if you like. Uh, and now I'll hand it over to Diogo to talk to us about the evolution of Venus.
Okay, so I think you need to stop sharing. Yeah. Okay. Oops. Okay, so I hope you can see my screen. Yes, continue to share.
Yes.
Okay, perfect. Okay, so I'll also put a timer such that I'm actually on time. Okay, so thank you so much. Thank you so much for the for the invitation. Um, And thank you so much for organizing. It's really nice, you guys are so well organized. As I also organize seminars, so you're an inspiration, So thank you so much. Okay, so today I'm going to be talking about Venus, and let me go back to my title. It's always a good place to start when you want to explain what you're going to be talking about. Okay, so this is the title of my talk today. So it's the influence of bulk composition and that lava flows on the long-term evolution of Venus. Okay, so I color coded the two things I'm going to be talking about. So I'll start by talking, of course, why do we care about what I do? It's not, it's for you, but also for me. It's important to remind myself why I do this. And then I'm going to be talking about two things and how they affect the evolution of Venus. So one is the bulk composition, that is the composition of Venus and its internal structure. And then it's the lava flows. You will see what I mean by this later. And then I'll finish with some open questions, and hopefully this will help the discussion that we have at the end of the talk. So I want to also mention two things. When I talk about long-term evolution, I really mean billions of years of evolution. So often when you'll see my models, they run for, 4.5 billion years of evolution. That is the age of, the Earth and Venus. And when I mean Venus, I often mean a Venus-like planet, right? Because what I'm really interested in is to understand this dichotomy between Earth-like planets and Venus-like planets. So, okay, I'll start. Why do we care? So this is the mandatory slide about how many exoplanets exist. Okay, so I actually went on Monday to this exoplanet.eu and I updated the number of exoplanets. So this is the chart of the number of exoplanets that have been confirmed over the years. So this is since 1990. And so you see that there's more than, 7,800 confirmed exoplanets, and there is more. There are candidates to also be, confirmed as exoplanets. You can see this is just a graph that shows an artist's depiction of all these potential exoplanets. Now, the important thing is that many of them are probably rocky planets. Okay, so like the rocky planets in our solar system, that means they are composed of an iron core and a silicate mantle. So it's always important when we talk about exoplanets to take a step back and actually look at, how actually diverse the planets are in our, even in our solar system. So, they have different sizes, they have different states. That means they've had different evolutions. But very importantly is this distinction between Venus and the Earth, right? So the Earth has, oceans and life. It has plate tectonics. On Venus, it's completely different. So I actually put this slide, which is some similarities between Earth and Venus. Okay, so this is our closest, one of the closest planets to us. So it should be, in principle, very similar. And so what you see is that, the position in the solar system, of course, is, very similar. The distance is not so different. The radius and the mass are quite similar. Venus is a bit smaller and therefore, has less mass. The surface gravity is a little smaller. The density is also slightly smaller. And also, even in terms of the orbit, so 1 year, that is when it goes around the sun, it's relatively similar. And this is where it stops. So then things get quite different. So while on Earth, the rotation period, there is 1 day, is about 24 hours. On Venus, this takes 243 days. So, in fact, a day on Venus is longer than a year, which has actually it brings issues because it's harder to look at things like moment of inertia, and other things that give us geophysical indicators of the interior of Venus. The surface temperature is very different. So you can see it's much hotter, it goes from 14 on average to 464 Celsius. And the surface pressure is also, immensely higher. So on Earth, we have about 100 kilopascals, while on Venus is more than 9,000. And part of this is because the density, so the atmosphere of Venus is much denser and is mostly composed of CO2. So the idea is that there's got to be something in the evolution of these planets that led them to have, you know, these many differences. And so this is part of my work is to try to understand this difference, this dichotomy. Okay, so what do we know about Venus and in particular Venus surface composition? So it turns out that actually there were some landers on Venus. So this is from the Soviet Venera missions. They departed in I think 1982, arrived in 1983, and in fact they survived about 2 hours on the surface of Venus, which is really cool because we actually have some photos from the surface of Venus. So this is from Venera 13. This is from Venera 14. And there was a spectrometer in these missions that actually measured the oxide composition of the surface rocks of Venus, which is really cool. Now, they have, very big errors, as you can see. So, for example, here is about 50%, but it's incredible that even lasting 2 hours, they send this information back to Earth. And what they found is that Venera 13 rocks, so the landing rock, and this is, of course, 2 points. One is about gabbros and the other one is basalt. So the most likely process responsible for the formation of rock is volcanic eruptions, just like on Earth. And so this gives you a sense of the activity and the evolution of Venus already. Now, if you want to look beyond the surface composition, there is huge uncertainty. So, for example, this study, which is Shah et al., this is from 2022, so it's a recent paper. They come up with three sets of models that can fit the moment of inertia for Venus. And this is, of course, compared to the Earth. So, if you have a sulfur-rich core, so that means that it's lower density and can be much bigger. This is contrasted to a sulfur-free core. So sulfur-free, so you have no light elements, which means that it's pure iron, so you can accommodate a smaller core. And then there's these nominal cases, which are more Earth-like. So what they find is that, for models that are acceptable and can fit moment of inertia of Venus, the size of the core can range from 2,900 kilometers to 4,250. So this is a huge uncertainty, again, for a planet that's right next to us. And that's, it's quite striking. So the first part of the talk, I will be asking the question, does this internal structure and the composition has any effect on the evolution of Venus? So this will be the first part of the talk. Um, and I'll get there in a bit. The other second topic I'll be talking about is about lava flows. Now, why does this matter? So we know that on Earth, lava flows typically range from something like 1 to 10 kilometers. So this is the order of magnitude. There's some rare flows that will reach hundreds of kilometers, but on Venus, it's very common that these lava flows are much longer. Okay, so you can maybe between 100 and 600 kilometers long. So some examples here. If you see light material here, this is a lava flow. So you see that in this Terceto Corona, you have something like a 750 kilometer lava flow on this side here. So it's a little hidden, but this is the lava flow here. This is in this place called Ningyu Fluctus, and it ranges for maybe about 600, 700 kilometers. And then there is the most striking lava flow that we know on Venus, which is this Baltis Valleys. And it extends for more than 6,800, so maybe up to 7,000 kilometers, and it occupies a significant portion of the surface of Venus. So that's really incredible. So the second question will be, does this length, so these longer lava flows, influence the evolution and dynamics of a Venus-like planet? And in particular, there is uncertainties regarding what is the state of the surface of the planet. Okay. So if you hear about tectonic regime, it's just really the surface expression of the interior dynamics of a planet. And for a long time, people thought that Venus was what's called a stagnant. There is an old, crust lithosphere that, doesn't move and is just relatively old and it's battered by impacts. And then people moved on to this kind of episodic lead regime. This came from the fact that it turns out that it looks like the surface of Venus is somehow homogeneous in terms of ages. And so what you have is a stagnant lead that becomes unstable and very quickly in geological time will basically subduct and to the interior. So you see the material here going into the interior and settling around the core mantle boundary. And then more recently, you start moving to this kind of regimes, plutonic-squishy lead regime, where you basically have your surface split because of intrusive magmatism into smaller blocks that move in relation to each other, and this creates some surface deformation, some surface deformation, and it's really controlled by drippings and delamination. So you have a very active interior of the planet. Okay, and so again, and this comes back to the length of the lava flows. Can the lava flows influence what we see and transition from in between these different regimes in terms of a Venus-like planet? Okay, so the first part, the influence of bulk composition on the long-term evolution of Venus. I'll show the methods very briefly, and then I'll show you some results and conclusions. So what we do from this paper that I show you, the Shah et al. 2022, we take 10 cases. So they will range from sulfur-rich big cores to small sulfur-free cores, and then we'll introduce these compositions into the mantle convection core, which is coupled to a core and surface evolution, which is called a StagYY. So this is the mantle convection code. So we will model three different regimes. So these three that I showed you and just explained. And the way you kind of control how they exist is by changing parameters in these models. One of them is called the yield stress, which is you can imagine as the surface stress that you need to break your lead. So, the higher this value is, the less deformation you have at the surface because it's harder to break the rock and initiate subduction. And then if you, also change the extrusion rate, which is basically if you have a melt being formed, part of it is erupted to the surface and cools down, part of it is intruded into the crust. And so depending on if you have a lot of eruption, there is volcanism, this will change the dynamics that you observe at the surface of the planet. So if you have a lot of intrusion, your lead will be more deformable, will be more squishy, and that's where this plutonic-squishy lead model comes from. Okay, I'll start by showing a movie of what these simulations look like. So this you can imagine as is basically a cut through the equator of Venus or a Venus-like planet. This is for in particular a small sulfur-free core. So it would be an iron pure iron core. And for an intermediate yield stress, which means that you will actually observe subduction and your lead moving around. So here you have temperature. This is basalt. If you see red, there is basaltic material. If you see dark blue, this is depleted mantle, which means you cannot keep erupting out of it. This is the melt fraction, and this is the viscosity. And the time is here in billion years. So what you see is that, you start, the usual mantle convection, you have plumes, and then what happens is you form a basaltic crust that, because of the low yield stress, is unstable. And so you end up basically having all the time these kind of, episodes of drippings and delaminations. This is different from the Earth because it's much more short-lived. But they also come in spurs generally. So you have some time where the crust is being built, and then it will tend to just subduct into the interior, and you end up building this layer of basaltic material around the core mantle boundary, which has some partial melt, and this is perhaps akin to what we observe on Earth with the large low velocity provinces, right, that we observe from seismic studies. Now, I'll show you kind of the end members of the models that we can see. So on the top row, what you see is small sulfur-free cores. So you see the small core compared to the simulations at the bottom. What you see on the left is for eruption rate of 100%. So all the melt that is generated above the depth of neutral buoyancy of melt will be erupted. If you see on the right 20%, it means that 80% of the melt is intruded throughout the crust, and only 20% will erupt at the surface. And you see that in this case, you have an yield stress of infinity, so you do not expect any subduction. And what you see is that you have a quite stratified system. So you have, in this case, a thicker crust, basaltic crust. This is because you're erupting much more than in this case on the right. And if you have a lot of intrusion, actually you weaken your crust system, and so you end up with these strippings that I showed on a movie before. And so a lot of this basaltic material will end up settling towards the core mantle boundary. So you basically have a different structure that arises from the fact that you have different ratios of intrusion to extrusion. Now, if you have a big sulfur rich core, so you can see that the core is much bigger, the mantle is much thinner. And what you see is that in that case, and again, the yield stress is lower here, which means you expect a lot of subduction, if you will, or drippings. And so in this case, basically, first of all, the mantle is much thinner. You have less availability of basalt. So you might have a thin crust, but most of the basalt ends up around the core mantle boundary. And so you again have this kind of stratified system. So if you try to put these models together, and so there is a number of models, I think maybe 40 models that I run with different yield stresses, different intrusion to extrusion ratios, and different sizes of the core. What you see is that you can then start grouping them. Okay, so what you see is that what I'm showing here is the temperature of the upper mantle below the lid. So you can just see it as a representative temperature of the mantle. And I'm dividing the models here from small cores to medium cores, more Earth-like to big cores. And on the bottom image here, I'm separating them by surface yield stress. So if you have infinity, you don't expect subduction. And then the lower the surface yield stress is, the more subduction you expect. So what you see is very clearly that the size of the core matters for the temperature of the mantle. So this has the strongest influence on mantle temperatures. So this has, because, if you have different convection, because, basically the convection velocities, if you will, depend on the thickness of the mantle. So you have slower convection and it's harder to melt for thinner mantles. And so this leads to higher internal temperatures, so for bigger cores. And then the yield stress has a lesser impact. And note that even if sometimes people think that because you don't have subduction, the planet does not cool efficiently. But this is partially true. But actually, as long as you have, a melting and crustal production, as long as you have volcanism, um, the planet can actually cool quite efficiently. So what you see is that it is true that a planet that experiences no subduction or less will have a hotter mantle. That difference is not that high as when basically, for example, you have different core sizes. So this is in terms of mobility now. So mobility you can imagine as the surface velocities divided by the interior velocities. So if you have a stagnant lead, for example, where you don't have surface velocities, mobility will be zero. If your surface velocities are, similar to your interior velocities, then mobility will be around one or higher. So what you see in this case is basically that mobility is actually higher for thinner mantles, so for big sulfur-rich cores, and this is because the mantle is hotter, as I showed in the previous slide. So more basalt is also available closer to the surface, and melting can proceed efficiently over time. And this melting actually, because you form crust, you have this chance as basalt transitions into eclogite, you have that extra weight that actually drags material down into the mantle. Mobility, of course, decreases with increasing yield stress. This is not a surprise because, if you have higher surface yield stress, it's harder to break the surface rocks, and so it's harder to initiate subduction. So basically, if you have, an infinity, if you will, surface yield stress, you would actually expect no subduction at all. But this is not always true because even for no plasticity, there is some mobility because of this intrusion. So in the plutonic-squishy lead, actually the weakening factor is actually intrusion. So this intrusion makes your lithosphere, your crust, squishy, and so it can actually delaminate and drip, and you'll have small but still present surface velocities. Finally, I'll talk about erupta. So erupta is just the integrated eruption rate over 4.5 billion years. So it's in mantle volumes. So, it's many times basically you can erupt your mantle throughout the evolution of a planet. And so what you see is that actually for of course, for big cores, which means thinner mantles, you have more erupta, okay? Because first of all, of course, the mantle is smaller, but also this mantle is warmer. And again, more basalt is also available closer to the surface, which will lead to more mobilities, more movement. And so this will lead to more eruption rate. And then it will decrease with increasing yield stress. So this is because if you have less overturns, there is less subduction, this leads to less volcanism. Because when you throw some material into the mantle, there is return flow and you expect some eruption to happen. Finally, I computed the love numbers, which, it's an observable. And basically, so the K2, this is a measure of mantle rigidity. And as I described here, is a measure of how easy it is to deform the body on a big spatial scale. So this has to do basically with, how the layers of your planet. So how big is your core, how big is your mantle. And what is, I think, interesting is that, so in this graph here, I show for different models that range from a big core, big sulfur-rich core, to a small sulfur-free core, so pure iron. I show what is the K2s that are computed from our models. The blue line here is the K2 for the Earth. It's very well known, so there is no uncertainty. And the K2 for Venus, it's the average value. It's the black dashed line here, and then the gray shaded area is the uncertainty. So again, Venus has huge uncertainties in terms of this kind of measurements. And so it's still interesting because what you see from our models is that actually these small pure iron cores or these big sulfur-rich cores, they don't fit within the K2 observed for Venus, even given this huge uncertainty. So perhaps not very surprising is that the core of Venus should be more in line to these medium cores, which again are more similar to the Earth. So the size of the core of Venus should be relatively similar to the size of the core of the Earth. But you can see kind of some maybe deviation. Maybe there is something there, maybe not. In fact, with the new missions to Venus, we'll get this K2 with quite high accuracy. So we'll probably be able to distinguish between these internal structures, but also perhaps between the tectonic regime, because as I showed you, different tectonic regimes lead to different mantle stratifications, where basalt can be more or less present towards the core mantle boundary. So maybe we'll be able to see something there. But this is, completely speculation. Okay, so the conclusions for this first part. So variations in bulk composition do affect mantle temperatures, and you expect larger sulfur-rich cores that will lead to hotter mantles. There is complex interplays between mantle temperature, the evolution of the mantle, local basalt enrichment, and tectonic regime. And this will, of course, have important implications, not just for the eruption rate, but volatile outgassing, which basically potentially will lead to different types of atmosphere being built, depending on not just your tectonic regime, but also on potentially the size of your core. And then finally, calculated K2 values, they favor medium-sized cores that contain some light elements, which are more Earth-like. Okay, so I'll move on to the second part of the talk, which is the influence of lava flows, again, on the long-term evolution of a Venus-like planet. So what do we do? So typically, in our numerical models, when you treat eruption, so if you have a plume, all the eruption will be vertical. Okay, so that means that whatever you're erupting is erupting on a small range of space, so on a small spreading angle. Okay, so if I talk about small lava spreading angles, that means more vertical eruptions. And then if I talk about higher spreading angles, that means that basically, if you have eruption above this plume, this lava will basically just flow for basically a longer space, therefore a higher spreading angle at the surface of Venus. We will test also yield stress, which it's every modulus of yield stress. So again, this is your stress that is needed to break the crust or your lithosphere at the surface of Venus or Venus-like planet. And then we'll try different spreading angles for lava flow. So 0, there is vertical eruptions, and then they will increase for 4, 15, 60, 90, and 180 degrees. It turns out that on Venus, about one degree spreading angle is about 100 kilometers. So basically, this would be 400 kilometers, 1500, 6000, 9000. So if you start approaching these higher values, they become less realistic, but it's still, interesting to try. And again, we're going to try these different models running the StagYY mantle convection code. Okay, I'll start again by showing you some, this is a bit of a repetition, but I think it's really important I think it's the sort of thing that these models really can build intuition on, which is what these different tectonic regimes that arise from different, basically, yield stresses. So much easier to break your surface here. This is harder. And so what you end up with is, in this case, if you have mobile leads, so you have constant subduction, you see that basically, well, first of all, your metal is much colder here compared to this case of a stagnant lead. And you also have this some accumulation of basalt, but your interior is well mixed because of this subduction or drippings. In this case, the stagnant lead, you build a thick basaltic crust at the surface, and then you end up with some material at the core mantle boundary, but otherwise the mantle is quite depleted. Now, if you start looking at the differences that the spreading angle leads to, so what I'm showing here is again your mantle temperature or internal temperature for two different yield stresses. So a low one and this one, 140 would be maybe intermediate. And then what you see is for like the reddish colors would be low spreading angles, more vertical eruption. And if you see bluer lines, that is for higher spreading angles, there is lava flows that are much longer at the surface of Venus. So you see that for small yield stresses, I mean, there is some difference, but this difference is not very pronounced. There is a different kind of temperatures at the end, there's a range of temperatures, but the behavior is relatively similar. It's way more interesting for these intermediate yield stresses where you see that actually the lines have quite different behaviors. So what you see is that for small spreading angles, so for the reddish colors, you have your internal temperature kind of slowly but steadily going down. So what this means, in terms of dynamics of the surface, is that you have constant drippings and lamination. They are small, okay, so very localized, but they are cooling the mantle. As you increase your spreading angle to larger, so for longer lava flows, you will transition from this more localized dripping and lamination to this much bigger kinks in temperature, in mantle temperature. So what this is basically big overturns of your lead. So this is what people call episodic lead, where you basically have a stagnant lead, and then over time it will break. And as you break and sink all this lithosphere into the interior of your planet, you have return flow, you have a lot of melting, and so your planet will cool down very quickly and a lot in this very small space of time. And then as you have a stagnant lead building up, maybe the temperatures will recover in the interior because it's harder to lose heat. Um, but what is interesting is that you can see that you go again from these like small localized delaminations and drippings to some overturns, and then as you get to bluer colors, bigger and bigger overturns. And then eventually, as you have these very long lava flows, you actually move to a stagnant lead. So you see that the mantle temperature is actually not going down at all. So what this tells you is that basically the lava flow is actually controlling the dynamics of your surface and actually changing the tectonic regime that you observe from something that is, way more localized to big overturns to basically no overturns at all. In terms of erupta, so this is again the integrated eruption rate for the different models. So this is for increasing yield stress. This is for spreading angle, so very, very localized vertical eruption to larger and larger lava flows. And so that this also will affect your erupta history or eruption history of the planet for different spreading angles. So it tends to increase with decreasing spreading angle. So hotter mantles will lead to more volcanism over time. And then it will slightly increase with increasing yield stress. And this is very tied up to basically the temperature of your mantle. Finally, I want to just show you some mobility. So again, the mobility is your surface velocity divided by the interior velocity. But more interesting is to look at the surface velocity in this case. So this is the surface velocity for one case from 0 to 4.5 billion years. This is for a case where you'd actually expect um, little to no subduction because it's high yield stress. And what you see is that this is true for large lava flows. But if you have small lava flows, actually what happens is that you can localize your eruption much more. So you have the chance in evolution of these models where your crust will locally thicken to a point that is thicker than the transition from basalt to eclogite. Eclogite is heavier, and so because it's heavier, you have this extra basically weight on your crust that can basically drag your whole lid into the interior of the planet. So what's happening here is that if you have larger lava flows, you end up with a more smooth and homogeneous crust in terms of its thickness, while if you have more localized eruptions, you can actually grow randomly in a place this crust to be thick enough that it becomes unstable and tends to sink. So again, it turns out that, and I'll go to the conclusions, that the length of the lava flow in a planet can actually influence its surface and interior dynamics, and not just locally, but also it can affect its long-term evolution by changing these tectonic regimes that are active. And remember that different tectonic regimes lead to different temperatures and different interior structures of your planet. And this is because, so if you have extended lava flows, this may suppress lithospheric overturns. And I already talked about this one. Of course, this change can lead to different thermal and volcanic histories on a Venus-like planet. Okay, so I will now use this opportunity so as I was doing this presentation, I thought, okay, what are the open questions? What are the discussion points that we can use um, you know, in the discussion that will follow my presentation. And we should have plenty of time for this discussion. So first, I want to talk about some outstanding questions about Venus. So I think it's really important to understand that Venus is, and this really changed, I think, from like the 90s. Venus is an active planet. So not just in terms of tectonics, but also in terms of volcanism. And we had some papers in the last years that actually show that, probably some volcanoes have erupted very recently. So in the lifetime of the Magellan mission. But of course, many questions remain open. So of course, more data is needed, and we'll have the missions that will, give us a lot of new data. So for example, as I was showing you, we have all this uncertainty in terms of Venus interior structure because our data is not very good, but it's supposed to become much better. But still, the big question is, I think, about Venus is to compare Venus and Earth in terms of their habitability. So, what has caused these divergent evolutionary paths of Earth and Venus is still debated. When it happened is also debated. So, this is just an example of a proposal that basically says that this divergence has happened so very quickly within the lifetime of a magma ocean of Venus. So you have two planets that will start, around here, and then either one planet will build an atmosphere gradually as the magma ocean cools down, and so you end up with a more Earth-like case. Or you can also, like in other cases, build different atmospheres, or just completely lose the water and end up, in a different state. So the idea is, and this is still debated, when did the Earth and Venus diverge so much? The second outstanding questions, and there are many, is what is the composition of the surface of Venus? So of course, I showed you some 2 points of data, but Venus is actually quite diverse in terms of its surface. So not just you have the lowlands, which perhaps we can think as like the oceans, but you also have the highlands, which so they are elevated in terms of topography. They occupy maybe 20% of the surface of Venus. And then within these highlands, we have this material or these terrains that are called the tesserae. Tesserae are basically highly deformed terrains. We have no idea what are their compositions. We don't know how old they are, right? So if we try to compare them or perhaps make an analogy with continents on Earth, um, they maybe are much older than what we think the lowlands are. But of course, it's also interesting to try to think, if you have this kind of global tectonic regimes, does the presence of this material that, maybe I'll say continent-like, but we don't really know if they're continent-like in terms of composition, does it affect the evolution and the surface dynamics of Venus? Um, the second question I would like you to think about is again going back to these tectonic regimes. So this is a paper that deals with the divergence, if the divergent evolution between Mars, Earth, and Venus. It's in the treatise on geochemistry. And so what we proposed here is that, if you start putting these different tectonic regimes, in triangles, it's a great shape. So if you put on one end plate tectonics, so Earth-like, mobile, very mobile, versus stagnant. So this is a planet that doesn't experience subduction, has a very stiff and perhaps old lead. So you have Earth on one end, Mars and Mercury on the other one. And then on the other axis, you have the plutonic-squishy lead. And so it's unknown where Venus really sits within this line here. But we thought, are there observables that we could potentially link to interior dynamics, and the way they express at the surface. So of course, when you have more mobility of your lithosphere, you expect a higher heat flux. So that's why the heat flux will come kind of in this direction, because the heat flux is not just higher for plate tectonics, it's also higher for plutonic squishy. So if we have a means of measuring heat flux, so of course this is perhaps for a planet like Venus and closer that we can actually measure this kind of thing. So heat flux. Another one is surface yield stress. So as I said, hypothetically, if you could get rocks from this planet and you could do some tests and see how easy or harder it is to deform these rocks, we could have an idea about the surface yield stress. So this would also gives you an idea if we are sitting where we're seeing in this diagram. And then finally, hypothetically, if you could go to a planet and look at what is the intrusion to extrusion ratio, so how much of magma is, and you can see this potentially through some, just geology. Can we get an idea of the intrusion to extrusion ratio? And perhaps this tells us something about, again, where does a planet sit within this triangle? And also, again, how does this lead to different thermal and compositional evolutions of planets? And the final question, and I think this is it's a really important question. So how can we connect this idea of tectonic regimes with so the evolution of a planet to exoplanet observations? And of course, most of the direct data that we'll get from exoplanets are from their surfaces and, well, atmospheres really. So it's an older paper by now, but the idea is that you have model lines of what would be the relative transit depth, so versus wavelength. So for a methane atmosphere, for a water atmosphere, and for a CO2 atmosphere. And so then you could get an idea of what is the composition of the atmospheres of these planets. And then, I mean, so this is a paper that came out very recently. It's by Tim Lichtenberg. It's a really good paper. But he puts this as, for different compositions of planets in terms of their structure and their surface temperature, can we get an idea of the types of atmospheres that are built, right? So can we predict the composition of an exoplanet's atmosphere depending on the tectonic regime, interior dynamics, evolution, and composition? And so this is just to kind of give an idea of the sorts of eruption histories that these regimes lead to. So if you have a mobile lead, there is a plate tectonics on Earth or similar, where you have these big plates so that the surface is divided into plates, and there is kind of slow but steady surface velocity because of subduction. So what you see is that your surface velocity, this is average around the planet, and from 0 to 4.5 billion years, you see you have, so this is in log scale, but you see that you have a constant, well, not constant, but there is no big changes in the surface velocities that you observe. So it's maybe about 10 centimeters a year. Um, and so this leads to a kind of steady, constant eruption history of the planet. While if you look at the stagnantly planet, then your surface velocities are very small, your mobility is very small, right? So this is something like 10 to the minus 3 centimeters per year. And see that your eruption rate, first of all, is much it's much smaller than when compared to a mobile lead. So of course, this will lead to different uh, eruption histories that will lead to different atmospheric conditions in planets. And then if you start thinking about other systems, like for example, episodic lead, so what you see is that again, you have this big overturn. So you can see you have this big overturn where you go basically from no velocity to very high velocities. So like, hundreds of centimeters per year. And so your eruption rate history goes from, relatively small to very high. And this is, we know this is bad for life, right? So this is what we have, for example, on the Deccan traps, right? So these very large igneous provinces on Earth, and we know this is bad for life. So there was a lot of animals and plants that died because you have this injection of of gases that will go into the atmosphere very suddenly. Um, and finally, so if you look at plutonic-squishy lead, you have, sort of like small mobilities, but they're kind of constant over time. And this leads to also kind of a smaller eruption rates than other regimes, but they're also constant, especially compared to a stagnant lead. So I think what I'm trying to say here is, can we link different histories of evolution of a planet in terms of their tectonic regime and mantle dynamics to the type of atmospheres that we're building? And can we actually link that to observations? Because of course, if it is true that, in order to have a planet that is habitable and have life, we need this kind of, mobile lead. Is this a way that we can start looking and start trying to predict which planets we should pay more attention to or potential are habitable? So just a different way to look at that question. And okay, I'll stop here. And I think maybe the best is if I stop sharing, but I can go back to the slides if needed. Okay, thank you.
Great, thank you so much, Diogo. That was fascinating. Okay, we're gonna sorry, we're gonna move on to the question time. Does anybody have any questions? Uh, yeah, Angeli.
Hey, thank you so much for the great talk. This was really interesting. It
Thank
kind
you.
of got me thinking about like applying this to like super Earth and stuff, like you were saying at the end. And I was wondering all the trends that you mentioned, if you were to scale that to a more massive planet, like 5 or more Earth masses, like would you expect to see similar trends, or do you think that other factors would come into play and maybe switch things up?
Um, it's a great question. I think you would expect relatively similar trends. That'll be my expectation. Um, I think I mean, it's hard to, I think, predict the evolution will be quite different. I mean, of course, a bigger planet will probably take much longer to cool down, and especially the magma ocean stage should be, I think, much longer. So, I think if you could scale down, sorry, scale up in terms of time, I think you would see similar trends, or that is my expectation. Yeah.
Cool. Very interesting.
Of
Thanks.
course, if you move to other planets that have a lot of water, right, like sub-Neptunes, things will be very different. Yeah.
We have a question from Maxime.
Hi, Maxime.
Hi, can you hear me?
Yeah.
Yeah, great. Thanks, Diogo. That was really interesting.
Thank you.
I have a couple of questions.
Hmm.
The first one, yeah, let me think. The first one was about the spreading angle. Is that
Hmm.
a thermal effect or a compositional effect?
It's a compositional effect. Yeah.
Okay.
So you basically would take, yeah, sorry. Yeah, it's something that I should be able to explain better by now. But basically, the idea is that you have this material that is erupting so vertically, right, through this column, and then you will spread that material over a certain distance. Yeah. So we'll have thermal effects eventually, like, but it's not, it's a secondary effect. Yeah.
Okay. Okay, cool.
Yeah.
And my second question was, so I imagine that maybe I'm wrong, but these very large lava flows, do we think they're due to the lava, the erupted lava being less viscous, And so
Mhm.
does it mean that it's somehow produced at higher melt fraction and from maybe a hot amount?
Yeah, so I mean, so I think this is not settled, right? There's a bunch of factors. So that could be one, right? The mantle is hotter. Then, of course, the surface is much hotter too. So the lava takes longer to cool down and therefore moves longer. In terms of topography, Venus is also flatter than the Earth. And also you don't have things like, rivers and trees that will slow down these lava flows. And I think finally there is some indication that lavas on Venus might have a slightly different composition, so have more carbonatites, and so this would also make them basically, just take longer to cool down. Yeah. So I think there's a bunch of factors. They are all uncertain, but they all seem to point in the same direction, which is longer times at the surface. Yeah.
All right. Okay, thanks.
Thanks. I see Rob's hands up.
Yes. Diogo, thank you so much for a great presentation.
Thank you.
I actually want to hook into something you just mentioned, that on
Uh-huh.
Venus we think that we have more carbonatite melts. Is this a prediction or is this an observation?
You know what? I think it's an excellent question. I think it's an observation, but I couldn't point you to this. Let me see. I saw Paul Byrne was here. You would know this, but I don't know. Sorry, I can't answer that. I can't remember. Yeah, if it's like an observation, if it's a weak observation, or so you see there's Paul. Um, and it can also, of course, can just be local, right? We don't really know if it's like a global feature. Yeah.
Yeah, I thought it had to do with it being a low viscosity lava flow. Is
Yeah.
that someone else should totally step in.
It's
I
like an
think, yeah,
inferred thing. Yeah, that might
yeah,
be.
exactly. Because
Mhm.
I don't know, but I was actually going to ask something similar to Maurice, if that's okay, if I can just step in about, is there any connection between like how the length of these lava flows and something about maybe the outgassing, like the composition of volcanic gas, or how efficiently it can degas?
I can imagine so. Yeah. I don't know if there's a lot of studies that study this. I think people are starting to pay more attention, right? Not just in terms of um, how long these lavas are molten, but also in terms of what gases can really be outgassed for different temperature and pressure conditions. So I think it's like, it's like a circular argument. But it should matter. Yes. And also I can see in the chat, people said it's because we observe longer lava flows, so that's why we think they have different compositions. And then, yeah, Paul says the same thing, especially in the canali. So this Baltis Valleys is I think, a canali. So there's no chemical evidence, but I think it's like a way to explain these long lava flows. Yeah. I
Yeah,
also see that.
you reminded me to check the chat. We have some questions.
Yeah, there is one. Yeah.
Maybe I might just take this one before I forget. So we had a question from Robin Wordsworth. I don't know if Robin is actually here and wants to read the question, or if I should go ahead and read it. But it's okay. Have you considered including the effects of oxidation due to hydrogen escape on the surface composition in your models?
I have not. Yeah. I mean, yeah. I mean, yeah, I guess, a lot of these, of course, these models were really built for the Earth and not very Earth-like. This is something to think about. Yeah, it's also in terms of, I think the next step, and this is something we're working on in Zurich, which is to really try to connect your interior evolution with the outgassing. So not just tell you something about the eruption rate, but also about what would be the composition of the atmosphere. Yeah.
Cool. Let's take a question from Hannah.
Hi, thanks for a great talk. I was just wondering, you talked about these different core sizes, and I was wondering if you included like a feedback of having a larger core on the composition of the mantle, if you sequestered more iron into the core, or sulfur. Did you include how that might affect the composition of the mantle and its effect on its rheology and therefore its heat transport?
Yeah, I absolutely did. I thought I had a slide about that, but it disappeared. So I must have deleted it accidentally. but yes, so depending on your core composition, right? This will have an effect on your mantle composition too. So not just on your mantle composition in terms of availability or fertility of basalt, but also in terms of heat-producing elements, and also in terms of solidus and liquidus temperatures, both for the mantle and for the core, which means that we can also do some prediction about what would be, say, the size of your inner core, which is actually going into this love number calculation. But it's something I need to look deeper. But yes, it is being taken into account. Yeah. Yeah,
Great.
next time I'll have that slide in.
Thanks.
Cool. We have another question in the chat that's from Lewis Muller. I don't know if you're here, Lewis, and you want me to read it, or you want to ask. I can just do it. So the question is, if Diogo, if you kept your initial core mantle boundary temperature constant for all the models, or and what was that temperature?
No, it is evolving. So I can't remember exactly what is the initial CMB temperature, maybe like 4,000. But then, so what happens is, of course, we solve the equations within the mantle domain, but there is say a 1D or more like a 0D analytical solution for core evolution, okay? So what happens is that at every point at the bottom of your mantle, there is a consideration of the heat flux and also the crystallization of the core. So your core mantle temperature is definitely evolving, yeah. And I mean, this is outside the question, but it's also interesting to see how these piles of basaltic material that settle around the core mantle boundary will have an effect on the core evolution. Yeah.
Cool. I might ask another question actually. So what I was really interested in this talk, and I didn't know, is how many times over the mantle has been recycled in the squishy lid models. I was wondering also, I don't know if you have like volatile tracing in this model, but if you did, like, could you say something about not the recycling of volatiles as well as the silicate?
Yeah, I don't have it in this model. In principle, this is possible. Absolutely, yeah. So I mean, it is possible to just, I guess, track them as a passive tracer, but the most interesting thing would be to connect to an atmosphere model. Yeah, and this is again something that is, there's PhD students they're working on this in our group. Yeah. And this is, of course, again connects to the exoplanet observations, and that's really interesting. Yeah.
Cool. Okay. You have any more questions? Because I also have one more that I might just ask, if that's okay. But so you talked, I was really glad to see at the end tying this into exoplanet observations. And there's this point of like distinguishing high eruption rates and low eruption rates. And I'm wondering if you can think of like any actual observable things in the near term that might be able to distinguish this.
I don't think so. I mean, I think perhaps, right? I mean, okay. So we should, with the new missions for Venus, be able to distinguish at least between mafic and so between, I guess, basalts and granites or something like that. Now, hypothetically, if we would have enough definition, we could start looking at different types of magmatic rocks. And we know that some, right, we can distinguish between some that are more intrusive and some that are more extrusive, because eventually through just movements at the surface, these intrusive rocks will end up potentially coming to the surface. So I guess that would be the closest, but I wonder if we'll even have like the data, the definition to see these sort of things. So I'm not sure. Yeah.
Yeah. Just going back to the chat, we have Hannah's wanted to follow up on Lewis's question. Hannah, I don't know if you also want to, if you're still here and you want to ask yourself.
I'm still here. I just didn't want to take up all the questions.
That's okay.
People.
Yeah.
I was wondering, could you say you're tracking the evolution of the core, and that the kind of this periodic delamination up to the CMB is doing interesting things to the heat flux. So I was just wondering if you considered coupling it to any dynamo scaling laws to see if Venus could ever have had a magnetic field, or whether you could get any intermittent dynamo generation if you've got this stuff delaminating, because that could be pretty cool.
Yeah, that is true. So, I mean, we do track the CMB heat flux, right? So this is in principle possible. I haven't considered it, yeah. Yeah, I guess then it's just another complexity, right? In the sense that how detailed do you want this magnetic field generation be? So with StagYY, it has been done in the past. I think things like, okay, is the heat flux or heat flow high enough that you could create a magnetic field, for example? This was done for the Earth, but this could be done for Venus too. Yeah.
Great. Any final questions? Yeah, Rob?
This might be a bit more speculative, but I'm just thinking about the plutonic-squishy lid regime and how magma is intruded in the mid-crust. But then I'm wondering, to what degree will this magma maybe also react and interact with the rest of the crust and therefore evolve compositionally? Because I can imagine, like, there's also a question, like, how long or how quickly or how slowly does the magma then crystallize in the inside of the crust? Because there's a lot of time to crystallize and can also differentiate. You have like the first crystal settling down below, and then the more evolved melt settling up above. And if at some point then the newly formed part of the crust will eventually be exposed to the air, then maybe that also like mean that the rock that we see might not be fully representative for like this bulk magma that intruded. So do you know how long does the magma have to crystallize in the mid-crust?
So, I mean, yeah, first of all, I mean, the dream is to have that kind of resolution in our models. I mean, in global models, the resolution is never very high, which means it's hard to really understand small scale processes. I don't know what is really the time scale. I think the only thing I can tell you is that I think it's really time and mostly like where it's happening, right? So it depends on the eruptive history of that place, but also the tectonic history of that place. So I think if you're intruding into a block of, cold and old crust, it probably will crystallize faster. But if you are into like an active place that, it's like warmer or squishier, if you will, then, it will take longer to crystallize. If it does, maybe, it just tends to, lead to some dripping or something. Yeah. But yeah, I don't know. I guess you could do these kind of models if you have like a very high resolution and yeah, and someone really understands metrology.
Oh yeah, sounds like that's some more PhD projects for GFT.
Yeah.
Do we have any last minute questions, comments, big problems? No. Great, then I think we'll call it here. So let's thank Diogo again for an excellent talk and all of you for an excellent discussion.
Well, thank you.
Yeah, and we will see hopefully some of you here next month for a talk about radial velocity detections with Annelies Mortier. And thank you again so much. Bye.